What we're doing in chapter 1 for today is primarily looking at the ways that we look at and classify matter. So, by definition, matter is anything that occupies space and anything that has space, takes up space, has a mass. So pretty much any physical object that you can think of is matter. And chemistry is the study of that matter and its interactions. Now, where we can get confused as far as matter is concerned is when we start to look at things that aren't matter, things that are important to us, things that we will study, but are not physical objects. And energy is one of those things. Energy is not matter. Energy is often used to help us to transform matter, or is given off as a result of the transformation of matter, but it itself is not matter. Energy we can think of as the capacity or the ability to do some kind of work, whether it be to light this room or to compress air, to heat things. Those are all things that we would classify as being energetic. But none of those things actually meet the criteria that we're talking about. Energy does not take up space. Energy does not have a mass. What I want to start out today talking about, though, is I want us to look at and try to classify matter in the ways that we can. And so I'm going to open this up for discussion. If you're listening in on Zoom, you can participate in this as well. Either unmute yourself and interject, or drop a comment in the chat. What I'm looking for is this. What are some ways that you can think of that we can classify matter, that we can put matter into groups? So I'm going to ask you to talk to each other for a second with whoever's around, and let's try to come up with some ideas here. Let's brainstorm some stuff. So what are some ways that we can classify matter and put it into groups? All right, so Jackson has inputted a first idea here. I'll put it on the slide. Good starting point. We can classify matter based upon its phase. Is it a solid? Is it a liquid? Is it a gas? Is it one of those weird other kinds of substances? What other ways can we classify matter? Yes. So you should be able to find this PowerPoint in Blackboard. Let me break this out of this. If you go to content, it would be in the lectures folder, chapter 1 PowerPoint. All right. What are some other ways that we can classify matter? Phase is one way. What are some other ways? How can we put matter into groups? Yes. Okay. What do you mean by that? Okay. Someone's been reading ahead a little bit. That's fine. Any other ways? Okay, so these are probably the two most common ways of doing it, by composition or by phase. Now within these, we could probably think of other ways as well. For example, could we classify based upon these substances over here are metals and these substances are nonmetals? Could we look at them in terms of some of their physical properties? These are blue objects, these are red objects, these are green objects. These are hard, these are soft. There are lots of ways of classifying matter. But what we're going to get into today primarily is the second of those. And the second of those is classifying by composition. And so for this, you're going to need to construct a flow chart somewhere in your notes. It's going to look something like this, where we have matter at the top of the pyramid, and we've got some things kind of branching out from underneath it. And so for this, I'm going to flip over to our whiteboard here, and we're going to construct this right here and now. So at the top of our flow chart is going to be matter. Now we can break matter down into two subcategories based upon its composition. Matter can either be a pure substance, and in a pure substance, all of the atoms or molecules look the same, or we can have a mixture. Where different parts of the sample will look different from each other. Now, within a pure substance, we can split this into two groups as well. Anyone think about what the two different types of groups might be for pure substances? Yes. Okay, that's actually the mixtures. For a pure substance, remember, everything has to look identical. So, yes? I'm sorry, I didn't hear. Element is one of them. In elements, all of the atoms are the same. The other kind is the compound. And in the compound, we have chemical combinations of elements in fixed whole number ratios. Now, what do I mean by that? What does that mean to have a fixed whole number ratio? Well, that means that for a chemical compound to exist, it has to be made up of the same elements combined in the same way every single time. Anybody, tell me the formula for water. H2O. What that means is that every single water molecule has 2 hydrogen atoms and 1 oxygen atom. Every single one of them. 2 hydrogens, 1 oxygen. That's a fixed whole number ratio. To deviate off of that means that I no longer have water. If it's 2 hydrogens and 2 oxygens, it's no longer water. It's now hydrogen peroxide. Very different kinds of properties in terms of reactivity and, well, safety for that matter. So that's what sets a compound apart from an element. Element, all of the atoms are the same. Doesn't matter what it is, doesn't matter how it's combined, it is the same. So if I have a sample of tungsten, every single atom in that sample of tungsten is going to look the same. It's all going to have some kind of familiar property to them that makes you look at it and say, oh, that's tungsten. And similarly, carbon dioxide, water, they have a fixed ratio of one element to the other. That's what makes them that particular compound. Now, within elements, we can actually break them down into further categories. This is largely based upon appearance and property. We have metals on one side and nonmetals on the other. And we'll get into some of the more subtle differences between those here in just a minute when we start to discuss, at least at first glance, the periodic table of elements. So those are your pure substances. On the pure substances, again, you're talking about things that have a constant composition, that have a constant appearance. Okay, we'll talk about those in a minute there, Jackson, about the metalloids. There are elements that kind of are in the middle of that. They kind of exhibit properties of both. But again, pure substances, we're talking about something where we have a set ratio, a set appearance, a set chemical composition, and the substance doesn't deviate from that composition. Mixtures, on the other hand, mixtures are said to have a variable composition. What that means is that different parts of the sample can look different. There are multiple substances present in a mixture. You're sitting in a mixture right now. The air that you breathe is a combination of a variety of different substances. You've got nitrogen, you've got oxygen, you've got carbon dioxide, you've got some trace amounts of other gases as well. Mostly it's those three though. But if I took a sample of the air, what I would see is that I would see different substances in it. The substances aren't combined with each other chemically, they're all present individually in the sample. And because of that, there is variability in that composition. So another way that we describe mixtures is by having variable composition. So on this side of the ledger, we talk a whole lot about constant composition. On the other side, here we talk a lot about variable composition. And within a mixture, there are two different kinds of mixtures that we can talk about here as well. We have this is where the other point was made. We have the homogeneous mixture. And in the homogeneous mixture, we have a uniform appearance. And on the other side, we have heterogeneous. And heterogeneous mixtures do not have a uniform appearance. They have a variable appearance. Primary difference between those, can you look at it? Can you look at it and see the different parts? So, for example, this bottle of hand sanitizer is a mixture of ethyl alcohol and a bunch of other ingredients like glycerin and some polymerizing agents to make it a gel. So there are compounds in this, but the whole thing would be classified as a mixture. If I were to take a sample of this, I would be able to extract the glycerin from the ethyl alcohol, from the water, from the fragrance. It might take some doing, but we could do it. Every single one of the chemical substances in this hand sanitizer has its own identity. I can take the top off, I can smell it, and it smells like ethyl alcohol. Also smells like whatever fragrance they put in there, but you can smell the alcohol that's in it. Yet, if I was going just off of its appearance, I couldn't pick out any of those components individually on their own. That's what we mean by homogeneous. From an appearance standpoint, I can't tell any of the parts of it as being different from each other. But from a chemical standpoint, I know that there are many substances in here that are different. Heterogeneous, on the other hand, lacks that uniformity. I pick it up, and I can look at it and see, oh, here's this component, here's that component. That's the primary difference between them. So any questions at this point about how we can classify or separate the different types of matter from each other from this compositional standpoint? So if you're looking at the PowerPoint, if you're going to look at it later, you can see that all of the stuff that we just discussed and put into that flow chart, all is available in long form in this PowerPoint. talking about the different types of pure substances, what makes an element different from a compound. We will stop and talk here about elements for just a second. One thing that we have to recognize about elements is that elements are substances that you cannot break down into simpler substances. Once we get down to the elemental phase, or the elemental compositional form, we can't break it down further than that, at least not without doing some serious nuclear kinds of processes. Every element that we know of is organized on the periodic table of elements. And there are 118 of them in total. Now, those 118 elements are broken down into some relative groups. We talked about before, the relative groups here are your metals, which tend to occupy this side of the periodic table. And your nonmetals, which tend to occupy this part of the table right here. Now, the spaces in between these ones that are shown here in green, starting with boron, kind of working the way through the middle of the table on this dark black staggered staircase between the two, these are referred to as your metalloids. Metalloids generally tend to fall into one category or the other. They tend to have tendencies that are more usually non-metallic than metallic, but they're classified in this way because they do exhibit some properties of both areas. So silicon, for example. Silicon is usually found in molecular substances like a nonmetal. It is brittle like a nonmetal, but it has a shininess like a metal does. It can conduct electricity like a metal does. And especially if we get it down to low temperatures and really pure kinds of substances, silicon is actually really good at conducting electricity. And it's one of the reasons why we find silicon in a lot of microprocessing chips, because of that conductivity and its weight and its lack of corrodability compared to, say, copper metal, aluminum metal, or any other metal for that matter. So we'll talk more about these in a later chapter. I did want to kind of introduce you to them because there is some viability, there is some stuff that we can get into with those. And so based upon what you know about metals and nonmetals already, let's look at each of these substances and try to identify whether it is metallic or non-metallic based upon its physical properties. So when it comes to physical properties, what kinds of things are we looking for out of metals? Okay, shininess. Okay, might be a little hard to see in a picture, but yes, density would be something we look for in metals. Okay, conductivity would be another good one. Anything else we can think of? Softness, I'm assuming you're referring more to things like flexibility, bendability. So let's look. From this standpoint, would we consider phosphorus to be a metal or a non-metal? Right, it's David, right? Okay, why is phosphorus a non-metal? Okay, not shiny, doesn't have any of the physical characteristics. If I'm looking at it, doesn't really exhibit anything that I would say, oh, that's definitely metallic. Okay, so put an N next to that one. What about the copper? All right, copper would be a metal. Probably not the best picture of it here in terms of showing its shininess. But based on what we know about copper, we know that it does have a shine to it. It does have conductivity to it. We would anticipate it being metallic. What about the bromine? So the bromine's in this vial here. Does it have a shininess to it? Not really. Does it look like it would conduct electricity as a liquid? Not really. So we'll call that a non-metal. Nickel. Nickel has a lot of the things that we were looking for. It's shiny. It looks like it's bendable, just based on how it's kind of set up there. So we'll call that a metal. Lead, shiny, flexible, metal. Gold, shiny, not showing flexibility here, but the ability to form many different shapes also can show that. So we show it here in bar form as well as in nugget form. Carbon. I mean, it's kind of shiny, maybe a little bit. Certainly not as shiny as any of the others. It does have a softness to it. If you're writing with a pencil right now, you can see that. Pencil lead is carbon graphite. But doesn't really conduct electricity. Certainly isn't as shiny as any of these other metal samples. It's kind of tricky, but non-metallic. Aluminum, we know from firsthand experience, aluminum can be drawn into sheets. That's what aluminum foil is. It's shiny, it's bendable, it's very easily manipulated. Not terribly dense as far as a solid is concerned, but it does meet all the other criteria. It's a metal. Sulfur, it's powdery, it's not very shiny, doesn't seem to do a whole lot. Non-metal. Tin, here we show it as rods. We've also seen it drawn into cans and foil. It's shiny, it's metallic. So any questions about classification of elements based upon physical kinds of properties? So as we mentioned before, metals can largely be distinguished from nonmetals based on two ideas: conductivity, and shininess, luster. Now, if we're just looking at each of them in terms of their physical properties without actually measuring anything, it's going to be pretty hard to figure out how well they conduct electricity. So shininess is kind of the way that we would have to do things. On the whole, nonmetals tend to be pretty dull. They tend to have relatively low luster. There are some exceptions. We talked a little bit about the metalloid silicon. We saw that graphite does have a little bit of a shine to it, and certainly carbon in diamond form has a lot of shine to it. It's able to reflect light very, very well. What we also tend to see is that when we have elements that are gases or liquids, they tend to be non-metallic. The one exception to that rule is mercury. Mercury is a liquid metal. It is the only liquid metal. But if we have gas samples, they are definitely going to be non-metallic. There's no such thing as a metallic gas sample. And there's only one example of a metallic liquid, mercury. So state of matter can play into this as well. We can look at something, look at its phase, and use that as kind of a drafting dodge to say, okay, this is a metal, it's solid and shiny. This is a non-metal, it's a gas, it's a liquid, it's a solid, but it's not shiny. As far as elements are concerned, we identify elements based upon their symbols. Their symbols are a 1 or 2 letter abbreviation for their name. Most elements do have a 2-letter symbol. There are some that have a 1-letter symbol. For the most part, we can kind of rationalize where a metal or a non-metal element symbol comes from. There are some exceptions to that. So for example, a lot of your metals are based upon their Latin names. So the reason why copper is Cu is that its Latin name is cuprum. And as in the Latin form, cuprum, Cu, is how that element is spelled. So that's where that comes from. Same thing for gold. Why is gold Au? Well, the original Latin name for gold was aurum, and Au is the beginning 2 letters of that word. For silver, argentum. Since Ar is already taken by argon, silver takes Ag based upon its Latin name, argentum. And this is pretty much the case for all the ones that seem kind of odd. Either we have the first letter of the element, the first 2 letters of the element, or some kind of combination of letters in the element's name, depending upon what's available and what's not. So nitrogen is N, neon is Ne, since N was already taken. Nickel is Ni, since N was already taken as well. We just go to the second letter. Where it gets confusing again is when we start getting into some of these ones, and these are very, very common elements. Your sodiums, your tins, your Now, when these come out, what we can see is that the atoms come together, and if they come together with different elements, that's when we go from being an element to a compound. So this right here, this is still elemental. We still consider this to be elemental oxygen. Even though it's not atomic, the samples within it are all of the same substance. Down here, now that we've combined the carbon and the oxygen together, now we are seeing molecular substances that would cross over into being compounds because they are no longer a single elemental sample. Now we've got carbon and oxygen combined together. It's still a compound. Every single one of these carbon dioxides has one carbon and two oxygens to it, but they are now combined together in a molecular substance, chemically speaking. So this is where we're going to stop for today. We'll talk a little bit more about compounds on Friday, and then we're going to kind of transition into talking a little bit about numbers. And that's going to be the primary focus of Friday's lecture is numbers, measurements, significant figures, because that'll get us very nicely into what we want to do over the weekend. Have a good day.